Imagine a world where electricity travels through wires without losing any energy. No wasted power, no overheating cables, no massive power losses across continents. Trains could float above tracks. Computers could become thousands of times faster. This might sound like science fiction, but scientists have been chasing this possibility for over 100 years. And the key lies in something called superconductivity. Electricity powers almost every part of modern civilization. From the smartphones in our pockets to the life-saving equipment in hospitals, from bustling factories to the global data centers that connect our world, it's the invisible force driving progress. But behind this modern marvel lies a fundamental and costly inefficiency, a hidden problem most people never notice. Whenever electricity moves through normal wires, a portion of that precious energy is inevitably lost, converted into wasted heat. This phenomenon is known as resistive heating. This happens at the atomic level. As electrons, the carriers of electrical charge, journey through a conductor, they constantly collide with the atoms of the material itself. Each collision impedes their flow and generates heat. Across the world, our power grids lose an estimated 5 to 10% of all generated electricity during transmission and distribution alone. That might not sound like a huge number, but when you scale it up to the entire planet, the losses are staggering. It represents hundreds of billions of dollars in wasted energy every single year, enough to power millions of homes. This inefficiency has driven scientists to ask a profound question for over a century. What if we could create a material that offered absolutely zero resistance to the flow of electricity? A perfect conductor. Part 2. The discovery of superconductors. In 1911, Dutch physicist Heike Kamerlingh Onnes made a surprising discovery. While cooling mercury to extremely low temperatures, he noticed something incredible. The electrical resistance suddenly dropped to zero. Electricity could flow forever without losing energy. This phenomenon was named superconductivity. Later discoveries revealed another strange property. Superconductors can repel magnetic fields, causing magnets to float above them. This effect is called the Meissner effect, and it's the reason why Maglev trains can levitate above tracks. Part 3. Real technology using superconductors. While the dream of a room-temperature superconductor is still on the horizon, the technology we have today is far from a mere laboratory curiosity. In fact, superconductors are already the hidden powerhouse behind some of the most advanced and impressive machines on the planet, pushing the boundaries of transportation, medicine, and fundamental science. For example, high-speed maglev trains in countries like Japan and China rely on superconducting magnets. These powerful magnets levitate the entire train, eliminating friction with the track and allowing for incredibly smooth, quiet journeys at speeds over 600 kilometers per hour. In medicine, hospitals use superconductors inside MRI scanner machines. The zero-resistance coils generate extremely powerful and stable magnetic fields, which are essential for creating detailed, high-resolution images of the human body's internal structures, revolutionizing medical diagnostics. And in the realm of pure discovery, particle accelerators like the Large Hadron Collider also depend on thousands of superconducting magnets to bend and guide particles at near light speed, enabling scientists to probe the fundamental building blocks of the universe. But there's one major limitation that connects all these incredible applications. Superconductors only work at extremely low temperatures, often colder than 200 degrees Celsius, a temperature far colder than any natural environment on Earth. Maintaining these temperatures requires complex and expensive cooling systems, known as cryogenics, which typically use liquid helium or liquid nitrogen as a refrigerant. This constant need for extreme cooling consumes a vast amount of energy and resources. The high cost and engineering complexity of these cryogenic systems are the primary barriers preventing wider adoption, making large-scale use very difficult and confining this revolutionary technology to specialized, high-value applications. For decades, scientists have been searching for something revolutionary, a room-temperature superconductor. This would be a material that conducts electricity with zero resistance at normal temperatures. If such a material becomes practical, the impact would be enormous. Power plants could transmit electricity across continents without losing energy. Electrical grids would become far more efficient, and devices could become dramatically more powerful. Some researchers even believe this could transform global energy systems. Part 5. Recent scientific progress. In recent years, the quest for a room-temperature superconductor has intensified, with scientists reporting several promising, yet contentious, breakthroughs. These moments generate huge excitement, but also highlight the immense difficulty of this scientific frontier. In 2020, for instance, researchers from the University of Rochester announced a stunning discovery, a material that showed superconductivity at around 15 degrees Celsius, a temperature you might find on a mild spring day. However, there was a monumental catch. It required extremely high pressure, millions of times Earth's atmospheric pressure, similar to conditions found deep inside gas giant planets. This made it completely impractical for everyday use, but it proved that superconductivity at warmer temperatures was physically possible. Then, in the summer of 2023, another material called LK99 captured the world's imagination. It attracted unprecedented global attention, spreading like wildfire across social media and news outlets. The initial claim was extraordinary, that LK99 might work as a superconductor at room temperature and normal atmospheric pressure. If true, it would be one of the biggest scientific discoveries in history. Laboratories worldwide raced to replicate the findings. But after weeks of intense investigation and peer review, the scientific community reached a consensus. Most laboratories concluded the evidence was not convincing, attributing the observed effects to other known physical properties, not superconductivity. This episode shows how challenging and sometimes frustrating the search really is. Science is a process of verification, and extraordinary claims require extraordinary evidence. Undeterred, scientists continue experimenting with new materials. They are exploring complex hydrogen-rich compounds under pressure and designing exotic crystals with the help of artificial intelligence, pushing the boundaries of what we know. The hunt is far from over. If room temperature superconductors become real and practical, the world could change dramatically. Electric power grids could become almost perfectly efficient. Electric vehicles could charge faster and travel farther. Computers could process data much faster with less energy. Powerful quantum computers might become easier to build. Even futuristic transportation systems like hyperloops and advanced maglev trains could become more common. Some experts believe this discovery could be as transformative as the invention of the transistor or the internet. Final thought. 8 Kraus, 830. For more than a century, scientists have been chasing the dream of perfect electrical conductivity. The goal is simple: a material where electricity flows forever, without resistance, without energy loss. We haven't fully achieved it yet. But if we do, it may not just improve our technology, it could reshape the entire future of energy on Earth.